Hello everyone. I hope you can see my screen and hear me okay. Um, Today I will be talking to you about part of my research, which is uh, on opportunities and challenges of conjugated materials in organic electronic applications. Before we dive into that, I want to just give you an overview about who I am. Basically, I'm a PhD candidate, finishing up my PhD at Georgia Tech. I work for Professor Seth Marder, and although I am a trained organic and polymer chemist, I've been mainly trying to take that onto the level of fabrication and devices. And today I'll share kind of part of my work to that end. But if you don't remember anything from the end of this talk, there are like three questions that I want to leave you with, and I'll pose them now before we dive in. So the first question is, well, these are conjugated organic polymers, so they are technically plastic, right? So why do we want a plastic to be conducting? And then what is my role as a scientist in this? And then how is my research impactful to the wider scientific community interested in these applications? So to answer the first question as to why we want this. So in the last 30 years, there has been an increasing interest in using organic materials into daily life applications, including, bioelectronics, solar cells, display technologies, like for example, the Samsung OLED technology. And, they have also been used as battery materials, as thermoelectric materials to generate electricity from the heat of your body. So these are all interesting applications where, although inorganic semiconductors have dominated that area in the past, we've been seeing a lot of opportunities for organic materials to actually provide that role for us. So the advantages of switching from something inorganic to something organic is due to their flexibility. So, we can have flexible devices. We can also have synthetic diversities to tune their properties because, if you're a chemist, you might know that you can change the properties of the material just by changing the functional groups on there and tweak and tune the processability, how it's processed, whether it's stable or not, just by a few modifications. Uh, so why do we care about, conjugated polymers? So if we look at something that is just a single double bond, you have the highest orbital being a pi and then an anti-orbital being a pi star. And as you start adding double bonds, you start getting this conjugated effect from the even odd type of thing where you have double bond, single bond, double bond. And then what that leads to happening is that you start getting the gap between the highest occupied orbital, which is this one, and the lowest unoccupied orbital to start to get narrower and narrower. And if you go to an oligomer, you're getting more conjugation. And then at the end of the day, if you go all the way to a polymer, you have this gap between the two orbitals becomes too close that you can no longer distinguish a single state. It is more of a band. And physicists normally love to talk about bands because they stem from the inorganic world, where basically, you have a continuous energy packet of filled orbitals versus a continuous packet of empty orbitals. And this is basically going to be kind of the main energy values that we work with, and that will kind of determine the properties that we'll discuss tonight. So now I would like to introduce the other concept, which is doping. So if you know the word doping from, inorganic chemistry or from just, having seen the word doping, you know that it is some form of substitution or addition of an impurity. So for organic materials, you can have doping in two ways. You basically are adding a molecule or a polymer impurity into your matrix of potentially semiconducting or conducting polymer. And what can happen is one of two things, is that if you have an electron-rich polymer, you'll have that polymer donate an electron into your dopant, your impurity, and then basically the absence of this electron will will induce charge transfer because then it can accept an electron from a neutral polymer that exists in the matrix. Now, on the other hand, if you have an electron poor polymer, what can happen is it can, what an electron poor polymer, which is represented here, what can happen is that you can get a transfer of electron from the dopant into the matrix so that you fill the unoccupied orbital, and then this kind of single electron that you just added can jump around into your system, inside your system. Now, just so that I'm not intellectually dishonest when I'm quantifying this about, you want it here, we show it to be, oh, this is just gonna go, because the energy difference makes it spontaneous, but that's not always the case. Sometimes you can get a system like this one over here where for the electron to go from this empty orbit, from this full orbital to this empty one, it's an uphill reaction. And that can happen, because we know how to activate these things via heat or light or some other stimulant that is appropriate to the system. Now, how has that benefited the scientific community, working on conjugated polymers within the last 40 to 50 years? So in the 1970s, 3 scientists discovered polyacetylene, and then they reported its conductivity denoted by sigma as something on the order of 10 to the power 5 Siemens per centimeter. Now, if you see this number and you don't know the context, you'll say, well, is it good or bad? This is kind of comparable to conductivities of copper and gold and silver, because these metals have conductivities above 10 to the power 4 Siemens per centimeter. So it's very conductive. And this is why, people now write grants trying to achieve metallic type conductivity, because they want to achieve values that are resembling metal by employing organic materials. However, when this was reported in the 70s, although it had high conductivity, it was not air stable. So you need to handle it under very specific environment. And the other thing is that it is difficult to process. So, if you're trying to make it into a stretchable foldable interface, that would not be possible because it's very brittle. Anyway, fast forward to 2021, and throughout, those 50 years, we had, throughout like the years of research, we built, not just me, the whole kind of community of researchers built complexity in the synthetic design of polymers and dopants. We have the diverse building blocks to choose from to make our conjugated materials. And then people started innovating in how they want to process them. Do you want to spray it? Do you want to print it? Do you want to paint it? And onto what substrate you want to put it on? And then that allows, for a greater diversity into which application you're targeting. So what we need now in 2021 is something that's conductive, that is easily processable, and it is environmentally stable, that, it has a long shelf life that, you can use over time, so that you don't need to throw it out every few minutes or every few hours. So what is the state of the art right now in terms of these materials? So as we discussed, since we have 2 types of doping, we will have 2 types of materials. So whole transport materials are the materials that we can oxidize easily with those dopants. And these are some examples of the most commonly used polymers we have, and they have been heavily researched. There's hundreds of papers on multiple of them, and we know a lot of information about them, as well as their dopants. So the type of conductivities we were able to achieve is between 100 all the way up to 10 to the power 5, and these are solution process. They are air stable, so we don't have a problem with kind of innovating in that space. And now kind of the more and more a graduate student mentions to their PI, oh, I want to work on, let's say, P3HT. Like, someone will roll their eyes because it's one of those things that's been studied to death, kind of thing. So it's now kind of getting harder to find the little things that haven't been discovered yet and talk about them. So this is a nice segue to the part which I'm presenting on tonight, which is the electron transport. So when you add an electron into a molecule, molecules tend to not like it, because normally that puts it into the LUMO, or the conduction band, and that that is very susceptible to oxidation by air. And you see all of these scary structures, but these are all kind of permutations that people have tried to achieve some high conductivities. And although, if you go back on slide, we talk about 100 to 10 to the power 5 in terms of these materials that we can oxidize. The ones that you can reduce, it's a nature type paper when you get above 1. So it's multiple orders of magnitude harder to get the levels of conductivities that is, desirable for metallic type stuff. Now, and then the dopants as well are challenging because there has been, a lot of research to find these dopants that I show here, because these are one of the few ones that are, earth stable. They do not just reverse, you don't get a reverse reaction and have them sublime out of your film. So these are a few of the examples that I and people previously in my lab or our collaborators have worked on. So, and this leads me to the next thing, that, okay, I've told you that we want something conductive, but, where do we start? How do we pick something? So people over the past 20 years as well have used a lot of organic materials in something called transistors. And the way you evaluate the properties of the transistor is through a charge carrier mobility, where basically, basically how fast do electrons propagate through a film of this polymer. So, but we know also from physics that conductivity is a product of the charge carrier density and the mobility, and E is just, the value of the charge, is 1.6 times 10 to the power minus 19 eV, unless I messed that up somehow, because I'm not a physicist. Anyway, so, these polymers, they are closed shell materials. They don't have any charge carriers intrinsic in them. So we can increase the charge carrier density by just putting dopants in and getting electron transfer. Now, the other challenge is actually to have those charge carriers stay where you want them to be. And that can happen through one thing. If you get an electron transfer, you want it to stay on the polymer. You don't want the reverse reaction to just happen very easily and then, for everything to get dedoped within minutes. And this is, a challenge for electron transport materials because they get oxidized just by being exposed to air. So you always have to work under inert atmosphere. Now, as for the mobility, this is, since we know that has already been done, so we have a lot of structures to pick out of, right? So we can, and the way for us to modify it, if we don't like any of the structures in the literature, we can design new polymer by modifying their backbone and by modifying the polymer dopant interactions. Because you can imagine when you have a doped polymer that is negatively charged and you have the counter ion which is positively charged, if the Coulombic forces are are too tightly bound, if these two charges are tightly bound, you cannot have your negative charge on the polymer just go wherever it needs to transport charges. It will stay bound. So this is one of the things that we try to address, or people in the literature have tried to address. So, and this is why my hypothesis when I started working on this was, okay, let's look in the literature and pick a polymer that has high mobility, and then dope it so I can increase its density and hopefully get a high conductivity, right? When you're a first year, you get too excited and think, if you're going to do your first project, it's going to be very successful. So let's see where that took us. So I picked this polymer from the literature, which has a charge carrier mobility of 8.5, which is one of the highest reported electron transport mobilities. And to pair it with, I wanted to investigate, how would different dopants react to it. So you see all of these different structures, and they do indeed have different properties. So for example, this ruthenium dimer, upon reaction, it will give this ruthenium ruthenium-based cation. However, this cation has a large volume. So, it will have a hard time kind of being innocent inside the film and not distracting the polymer chains from stacking properly on top of each other. Versus if you have these N-DMBI based compounds, The cation is more planar, although it is the same size technically, but it is less bulky, so it can go wherever it wants without being a problem. That's at least was our hypothesis when we first started this. Now the other thing is, if you might be wondering, well, this is a dimer where you can expect that this bond is very weak and it will break, so you get the cation. Sure, but here it's a hydride type of thing, and this is a problematic compound because it doesn't react at room temperature. It doesn't like the polymer very much. It will phase separate in it, when you cast it as a film, and also you need to heat it up. So phase separation is kind of very hard to avoid. So what you end up doing is you put multiple equivalents of this H guy in order to get very little dopant. So that's why I was intrigued to try the dimer so that we don't have to go through the whole effort and just get a clean electron transfer at room temperature. So how do I synthesize this polymer? And although this polymer is known, I just thought it is, worth for my organic degree and all the organic courses just to show a few reactions that I have done. So basically, you first start by getting a selenophene. You use ambutyl lithium and trimethylene chloride to stanolate. Then you couple it with the diammonium benzodiazole, and then you get this guy over here. Then using LDA and trimethylene chloride to stanolate. So this is one of my monomers, and then the other monomer is done by basically taking a brominated naphthalene dianhydride and then imidizing it to get the naphthalene diimide. And then you do a Suzuki Stille polymerization in order to get this polymer over here, which has a molecular weight of 42, which is, you'll say, well, this is not a polymer. It is a polymer from, a conjugated polymer standards. It has, what this 42 represents is 42 units in repetition, basically, because this has a high molecular weight. Now, as for the dopant, how do we synthesize it? We basically just take our amine and aldehyde. We do a condensation using an oxidizing agent to get our imidazole. And, we can do that in 10 gram scale. It has a very high yield. Then we alkylate it to put methyl groups over here. So this iodide compound has very low solubility. So if we want to make the H compound, we just use a sodium borohydride and we get the H compound in multiple grams. Now, the other way to go to get to the dimer is that we need to change the counter ion to get to something more soluble like PS6, and then we use a sodium amalgam to reduce it and get the dimer. Now, although the sodium amalgam, it's expensive, it's very kind of dangerous to use in the lab. You need to be very skilled, which thankfully I got used to after multiple failures. So I was actually able to recycle the amalgam, where you prepare a large batch of this and then you kind of react your organic, you remove your solvent plus the mixture, you keep the metal stuff in there, and then you add fresh solvent, fresh compound, and then you do that multiple times till you've exhausted your whole mercury. Then you can either separate or add more sodium to the mercury and go all over again. So you're not generating mercury waste over and over again. Now, one thing that we wanted to try, which didn't work, is if we could somehow make this H compound by making a cation and then anion and coupling them together to get a dimer, but that was not successful. But we have multi-gram scale of all of these, so this is kind of became a very easy thing after we optimized it. So now you might think, well, how are you gonna process your polymer that is probably a brick dust plus this dope plus this thing you call a dopant into something you can measure, right? So there are multiple approaches in the literature that people have optimized. So there is this thing called, so this is from another paper where they do it for another polymer, right? And what they do is basically you can either prepare two solutions, mix them together, and then make a film out of it, and then you do whatever you want with it on glass or ITO or whatever substrate you'd like. Some people have also managed to do it on conductive paper. Uh, Now, the other approach that you can use is you can, if your polymer is kind of not, it doesn't like to behave properly, and I'll explain that in a second, you can make a neat film out of it, then you soak it in your dopant solution, and you rely on the diffusion of the dopant into your film in order to get any kind of action going on, and then you get your doped film. Now, a third approach, which I did not do here or kind of investigate. What I did was basically you do the blended mixture to get the film, and then what you do is you kind of dope it further by soaking. So this is called like a hybrid approach. I haven't tried this because I didn't think it was useful for my case. So for my polymer, what was done and what you're going to see throughout this presentation is basically I made a neat film and then I dipped it inside the dopant solutions, and then I got the dope film. And you might ask me, well, why did you do this instead of just mixing them together and getting and putting this on glass? Well, because when you dope them and you have these ionic compounds, they do not like to stay in solution. They start becoming aggregates and they precipitate. So it just becomes a whole hassle in order to put them on a glass substrate properly without the whole thing just turning out to be a mess. Now, the only challenge you'll need is you need to find a solvent that doesn't dissolve your polymer but dissolves the dopant and everything else. But that was easy for my case. Now, let's start by looking, well, how are these different dopants are going to react with my polymer. So when I dope this PNBS over here with the N-DMBI dimer, you start seeing changes in the solution spectra. Again, these are hard to kind of pinpoint well what exactly is happening because there are a lot of charge transfer absorption between the different units donor and acceptor on the polymer. So, but what we rely on is kind of, well, is there a trend of something constantly increasing versus decreasing? And we see that in the solution state. So we know there is a reaction happening. Now, in the solid state, because again there are a lot of aggregates being formed, it's not as easy. But here, this absorption in the UV area, this is where the dopant ion absorb. So as we're using a higher concentration of the dopant solution, we're dipping in. We're getting a higher absorption. So we know there is incorporation going in, and we have slight changes in the absorption spectra. So we know there is changes. However, sorry. However, what about the other two dopants? So what I noticed is that with the hydride version of this N-DMBI, there is no reaction, and however with the ruthenium dimer there is reactivity. But I'm just not going to show it here so that we're not repeating the same thing. Now, when I went on and I wanted to characterize the microstructure of when I'm adding this impurity throughout the film, what is happening to my order. So what we notice here, this is kind of not a very pretty picture for anybody who's an inorganic chemist, but for us kind of organic polymer people, this is kind of amazing that we're able to get nice images. Normally, some people use a synchrotron, but we didn't have the access to that at that time, so I just used regular XRD instrument to get these patterns on the film. And what I observed is that basically, when you're at the pristine level or at low doping level, you have kind of broad, low intensity peaks. But then as you start increasing the doping to like 5 millimolar, your peaks start getting gain intensity and they start getting narrower. And then once you hit 7.5, it seems like such a sweet spot that, you just get this abrupt sharpening of the peak, they increase in intensity, but then as if, when you go beyond that, it just becomes an overkill and you kind of have too much dopant in there, so it disrupts your morphology. And now, since, this might seem too qualitative, I actually plotted, how is the intensity changing? It starts increasing slightly from, 0 to 5. It increases sharply at 7.5, then it starts decreasing. What was I going to say? So yeah, and then it starts decreasing. Now, as for the other, for the full width at half maximum, I wanted to track, how are the peaks changing. So yeah, how is the peak changing? So basically, uh, it becomes sharper and narrower as you get to sorry, it becomes wider as you first introduce your dopant because when you're adding an impurity, it needs to get in between two stacks. So it will basically just change how they're packed on top of one another. It will just cause a disruption of your microstructure. But these dopants can go wherever they want. They can go into the amorphous region. They can go into the crystalline region. So it seems that at this concentration at 7.5, there is this sweet spot of distribution in my film that you just get a crystalline material, and then beyond that, the peaks start widening again, uh, just due to excessive dopant. Because as I mentioned earlier, these two structures do not like each other, so they will try to phase separate if they have the option. But if it's an ion, it will be not as easy to phase separate from one another because of the Coulombic binding. Now, the next thing was to measure the conductivity. How is the conductivity changing? But before I get into that, I forgot to mention, what is happening to the ruthenium doped one. So since the N-DMBI had no reaction, I did not study it further. As for the ruthenium dimer, the moment you add very low, you dip it in a very low, you dip your polymer film in a very low modality ruthenium dimer, you just see your whole any diffraction pattern that you have kind of vanish, and you just see air scattering. And the reason for that is because when you have such a bulky dopant that has a large volume trying to diffuse in, it's just messing up all of the stacking that you already established in your polymer film. So although it's doping it, it is not maintaining the structural order, and that we know is not good for conductivity. And actually, when we went on and measured the conductivity, we did not get conductive films with the ruthenium dimer, which we knew was that although it was doped, it was not conductive because of this structural disorder that we had, because the charges could not move from one place to the other for us to measure how conductive they are. Now, how do I measure this conductivity? So basically, we use the van der Pol method. There are multiple methods to measure your conductivity, but this is the one we use. And the reason we use that with gold contact pads is to reduce contact resistance between your connections and the electrode and your polymer film. And what that allows you to do is you have voltage on two electrodes and then a current on two electrodes, and then it's coupled to a computer that just tells you the resistivity, and you plug it into the equation during that's already pre-programmed to give you a conductivity based on the thickness of your film. Now, so now you have the other choice to make, whether you want to measure it under vacuum or in air or under nitrogen. So what I wanted to do is I wanted to test whether this polymer is going to be actually air stable. So because my hypothesis was, well, if I want this to be used in applications, we need it to behave itself in air to some extent. To the extent that if you're trying to encapsulate it, to the extent that you can put another layer on top of it, or to assemble the whole device if you're using it in a solar cell. So when we measure the conductivity, we notice that at 0 millimolar, it's not conductive because organic polymers have very low charge carrier density, so it's not conductive. And the conductivity starts increasing to 7.5 millimolar, which, if you remember, it was the most crystalline film. So this was when all the stars aligned when we were doing these experiments. And then you get the maximum conductivity around 2 millisiemens per centimeter. Now, if you remember from earlier, when I said, the type of conductivity we want for a metallic type is 10 to the power 5. So this is 8 orders of magnitude less than what we want. However, you don't always need, the most conductive polymer film in the world, because for certain applications like, LED, you want it to just be conductive enough. Because if it's too conductive, then your charges will migrate too quickly and it might kill your device. Now, the other thing that we wanted to measure is that, well, how is conductivity changing in air? So we only exposed it to air for the first few minutes to our measurement, which we saw, it did not immediately decrease. There was a slow decrease over 75 minutes to half the value. So which, it displayed sufficient air conductivity to do all of our experiments in air, which was kind of another good thing about the study, that, we didn't need extra sophisticated glove boxes to do all of this, that we were just able to do it in air. And now the other thing is we wanted to investigate, how does the conductivity change with temperature? So metals normally their conductivity gets suppressed with increase in temperature. However, here, because this is inverse of temperature, you notice that with the increase in temperature, the conductivity actually increases. Now, from these different doping levels, if you do a fitting using, an Arrhenius model, what you can extract are two parameters. Your EA, which is basically what is the activation energy barrier for one electron to hop from one side to the other. So imagine, you have point A and point B, and, your electron needs to hop. And then, how much energy is the cost for it to hop. And, normally if it's around 25 millielectron volts, that's room temperature. So, it's nothing, it's negligible. But here it's like 10 times that. So that's a major contributing factor for our polymer film to not be conductive. So, this is the other facet of doing these experiments, that when you get something that's not conductive or that's disappointingly giving you disappointing values, you try to rationalize about why is this happening, what's going on. So you start with a pretty high activation energy barrier that can go up to 300 millielectron volts. And then, as you increase the doping, you're increasing conductivity. So you reduce the activation energy barrier, which is kind of normal. And then, of course, beyond that, your barrier is going to become harder, because it just means that your system is overdoped. There is just way too many impurities for your charge to find its destination. It just gets interrupted along the way. Now, as for sigma zero, sigma naught is basically something called like intrinsic conductivity. It's basically sort of like a pre-factor that tells you about the transport capability of your system. And normally you want your sigma naught to be as high as possible for you to get actually something pretty conductive when you dope it. But here we notice that it decreases with the increase in dopant, which means that, although we're getting a conductive system, this system just doesn't really like to be doped, because we just have a lot of disorder going on, and that is what's putting us back in terms of conductivity, although, we expected it to be pretty conductive. Now, so what is the big picture of this? So what we were able to learn is the insight into the properties of the high electron mobility polymer. And then we were able to achieve maximum conductivity of 2 millisiemens per centimeter in air, which was, pretty satisfactory for what we wanted to do. And then this change allowed us to change our approach to which polymer we wanted to choose. So now we want to opt for polymer systems that are maybe not necessarily as flexible, or that might have different miscibility properties that open to get different conductivities. And although it was only me presenting this work tonight, this work is not the work of one person. I'm in constant collaboration with a material science engineer, Sean Gregory, who is an engineer, and then we collaborated on doing the conductivity measurements, and he trained me on actually doing doing it myself, as well as I'd like to acknowledge Maxwell and Samik. Maxwell is my undergraduate mentee who also, and we collaborated on the dimer synthesis. And of course, I'd like to acknowledge my advisor, Seth Marder, my mentor, Steve Barlow, and of course, members of the Marder Lab. And with that, I'll be happy to take any questions. I hope I didn't speak too fast and make it too short.
No, you're good. That was a fantastic talk. All right.
Thanks.
So I'm going to go ahead and dive into the questions for the chat. If you have any additional questions that you want to get in, please feel free to do so. Okay, so first question is, what conditions did you try for your coupling that you mentioned was unsuccessful? Any CH activations?
I think CH activation. Oh, I think probably the person is referring to this. No, I didn't try. It was just an idea that my undergraduate was thinking about, whether we can correlate them, but then it would entail losing hydrogen gas, which I wasn't big on, and I thought it might have just been easier to go the regular route and reduce it with the sodium amalgam, because we were able to prove that we get a higher, like a high yield and a multi-gram scale, which is much more than we actually normally, we people use like a half a milligram of this, and it's enough for multiple months. So we just didn't pursue it further.
Okay. I'll go ahead and ask for Isaiah as well. That we have Isaiah Spate, who's a big mechanochemistry person. He wanted to ask if you gave any consideration to doing a milling instead of to make this product that you're showing here. That's one of his favorite things to ask.
Oh, I actually have not. I haven't tried that. We didn't think about it.
Yeah, he preaches the gospel of mechanochemistry. We've had some very entertaining talks featuring both him and some of his colleagues.
Yeah, I love mechanochemistry. There is this system that is some sort of like a ladder polymer, and you do a certain stress, and it kind of unzips as a it unzips as a zipper.
Oh, that's awesome. See, Isaiah, I'm telling you, man, you're doing the work. It's getting out there. Do you have any idea? You kind of touched on this a little bit, but I'll go ahead and ask the question anyway, just in case maybe there's a little more to go into. With the dopant concentration, where you showed the loss of crystallinity.
Yeah.
So can you talk a little bit more about why you think you see, like, you have the peak and then it drops off so dramatically beyond that point?
Yeah. So what we thought was happening is, you have your solid, this is the polymer, and then you're adding, these impurities on top of it, and then they can go wherever they want. They can go to crystalline areas or amorphous regions. So what I think is happening is, you get to this point where you already have enough cations that are just stacking, minding their own business between different chains of polymer, and then you're adding kind of as if imagine a pot that is already saturated, and then you're trying to add more, so everything will just go overflowing, and you'll get a mess in the kitchen.
I got you. Okay.
And that's what I think is happening.
Okay. I mean that would make sense for why it sort of suddenly goes away.
Especially that the dopant does not like the polymer. These two kind of always have solid state miscibility issues, and they like to go away from the face-to-face, basically.
Okay. So this may be a dumb question, but I'm a chemical engineer, not chemist, so.
That is a long question.
So you talked specifically about the ruthenium dimer that didn't work. Because it's so bulky that like you talked about, it kind of breaks up the stacking and ruins everything. Could you change the ligands such that they basically start to act like a conductive bridge? So instead of so you talked about how it sort of disrupts the electronic transport between the layers. Could you basically synthesize it such that it actually helps promote that conduction?
Oh, yeah, I never thought about that. But I think I don't know how much flexibility you have in the ligand, because
I have no idea either.
no, because what I think can happen is, if you kind of use less high field, if you use lower field ligand, it will not be as its reducing strength is going to change. So that's why, for example, I can't use something like cobaltocene, because it's not as reducing as the ruthenium dimer. Okay. So, but although this is not to say that the ruthenium dimer is garbage. It actually works great for other applications where there is more tolerance for a larger volume ruthenium, for a larger volume dopant. But we just noticed that this, with these specific systems that need to pack really tightly, that normally we don't really need something that is bulkier. They like something more planar that could just move around easily without disrupting everything else.
Okay. So where do you see this going? Like, what are the next steps that you think you would, whether it's you or somebody else picking it up?
Oh yeah, so I've already published this work.
Okay.
So what I have suggested is basically to kind of, one, you have the system is basically you have a lot of options for torsion and kinks in the
Mm-hmm.
polymer.
Mm-hmm.
So one of the things that that have been recently reported in the literature is to people try to rigidify the backbone through intermolecular bonds like hydrogen bonding or some form of backbone cross-linking in order to planarize
Mm-hmm.
it so that you get less defects in your system. And the other option is, so this is like a very new concept. What people have done is instead of electron, let me show it through this picture.
Mm-hmm.
So I'll try to draw it because it's a very cool idea that people are trying to do.
Okay.
So basically, what people have done. Oh, I don't think. Oh,
Yeah, there you
here it
go.
is.
Yep.
So let's say we have, you have multiple, you have this filled band
Mm-hmm.
basically, and then you have your empty band over here. So what people have done is basically, instead of adding electrons into your empty band,
Mm-hmm.
what they have done is basically they thought about it the reverse way. Well, let's oxidize this band to the extent that the valence band becomes kind of a pseudo empty band that has been reduced. So it's as
Okay.
if, tricking the polymer. So for example, what recently people have done is they took a similar analog to this guy. They oxidized it to the extent that, they fooled the energy levels into thinking, well, I'm now an electron deficient polymer. And this is how they were able to get something like more stable, more conductive.
Interesting.
But what I personally have been doing is focusing on some other systems that I could actually get more insight into their charge transport behavior. So recently, I'm currently working on a project to kind of investigate why does an empirical model not work for one of the polymers I tried to study, and
Okay.
now we have like a whole study on why does the model fail. So yeah, I think there are a lot of opportunities in for like people in the future to do this. Like if I start to outline them, I
Mm-hmm.
think if I look at the list of projects I wanted to do, but will never had the chance to do them, there is enough projects for like maybe 4 PhD students.
Nice. Hey, that's good. That's that means you did some good work.
I hope
Um,
so.
yeah. Has anybody taken? I mean, they've taken obviously some of these materials that you're showing here, but has anybody taken the polymer that you've described in this talk and actually put
hmm
it into like is it meant for like a solar cell or what
Yeah.
type of applications is it used
So
for?
So yeah, I made a similar. I made like smaller analogs of it, and we have put it into solar cells. That was another project I worked on
Mm,
to kind of substitute a conducting oxide, and we were able to get kind of 14%
wow.
efficiency in a perovskite solar cell. It wasn't. It's not like the best because now I think that the world record is 25%, but it was kind
Sure.
of the first example of substituting an oxide
Yeah,
with
exactly.
with an organic layer.
That's actually really cool. I mean, the original perovskites were only 3%, so I mean, certainly there's probably a lot of room to improve. That's really cool. Um, we got another question from the chat here. Do hyperconjugate supported systems still display functional conductivity? I'm hoping that
So
I'm hoping you understand that question because I don't.
the way I understand hyperconductivity is when you get when you have a sigma pi star, like one of these physical organic mysteries. I don't know for a fact that I've seen an example of a hyperconjugation doing conduct like displaying conductivity. If there is an example in your mind or like something, a specific molecule you're thinking of, so that I
Mhm.
can brainstorm it further, but I don't know on the top of my head that this is it has been done or is being done right now.
Okay, catch me if you have a specific molecule in mind. Feel free to follow up real quick. I'll ask a couple more things anyway. Um, I don't know if I can remember the question. Uh, shoot, train of thought's real slow today. I blame it on it being Friday. Um, So is the polymer that you made air stable? No, it's not air stable, correct? You showed that does show some loss of conductivity when exposed to air.
So yeah, so the polymer itself, without us adding electrons into it, is air stable. We only start getting in trouble when we make the backbone has multiple negative charges on it.
Okay, all right. Okay, so the person that asked about the hyperconjugate system says they're thinking something like a nitrogen to trimethyl silicon bond as an intermediate between the conjugate system.
Yeah, I haven't seen an example of these, done in terms of conductivity, but
Okay.
I don't know, maybe it's something I need to look into in case I
Okay.
haven't been paying attention to it.
Okay. I think so. I'll go ahead and invite the chat. Get any final questions in that you might have. Um, but in the meantime, I'll go ahead and start wrapping up. So again, Khaled, thank you very much for agreeing to do this talk. This is super interesting. I really enjoy learning about the organic polymers and the work that's being done there because like I said, I had a couple of friends that were doing it when I was a postdoc, and just the things that they were doing were really cool. And obviously, you are also doing some really interesting things too, because this is not just the synthesis of the molecules, but the way you test them and everything else is really really interesting stuff. And it's really cool to see. I mean, especially the conductivities. I mean, getting 10 to the 5 Siemens per centimeter is just crazy high. Um,
Yeah,
Go ahead.
no, I was saying that it was kind of mind blowing when I saw that number. Somebody reporting it recently, but I haven't tried reproducing their numbers. I'll keep it at that.
Sure, sure. Fair enough.
And that's something that's something I think that we always struggle with in this field, or in solar cells or devices, because
Yeah.
they are sensitive to so many factors. Like a little bit of dust can just mess up the whole thing. So
Oh yeah.
we always struggle with attempting to reproduce other people's data, and that's why we always have to be kind of to the extreme details of the details, trying to explain how we did everything, so that if someone else comes and tries to do it, they can
Hmm.
actually reproduce what we have done.
Yeah, 100%. Yeah, it's. I've seen a lot of, as you mentioned, like especially when it comes to solar cells. Even things like how you mask them can make a huge difference in the
Oh
performance.
yeah,
Just little things that you might not think about, but it makes a huge difference. So that's it's definitely something you got to pay attention to. So I think that's all the questions we've got tonight. But I do want to thank you again, Khaled. And if I could
my
get you to hang
pleasure.
on for just 1 second, we'll chat real quick after we go off stream. But thank you to everybody for coming out. I forgot to I'll drop the link for the Discord in the chat. If you are new and would like to join our Discord, please feel free to do so. It is just as friendly and low key as the stream itself. It also has channels for things like collaborations and help writing manuscripts or editing manuscripts or getting somebody to read over your manuscript, whatever you need. People are always happy to help out. You can also ask questions about. I know I have on multiple occasions dropped some questions in there to try and get some other people's opinions or thoughts, and people are always very friendly and eager to respond and help out. So please feel free to join that if you would like to. And we will see you back next week, I hope. I am still looking for a speaker, so if you are new here and would like to give a talk, please get in touch with me. You can shoot me a DM on Twitter at Meekins Lab, Meekins Lab, or you can join our Discord and drop a message in there. Or you can shoot me an email, meekins@sc.edu. Any of those ways is a good way to get in touch with me, and love to get more talks going. But I do plan on being back next week. We'll find somebody, and we'll go from there. I'm sure we'll have another fantastic talk, just as Khaled's was tonight. But in the meantime, get your shots, wear a mask, and we will See you hopefully back here next week. And thank you again for coming out. Have a great weekend.